Hello everyone. There is this cute little theorem on the plane that is called the law of cosines that concerns triangles. So if I start off with any triangle that doesn't necessarily have to be a right triangle, and I denote the angles of it as alpha, beta, gamma, and then the corresponding sides by A, C, and B, then the law of cosines tells me that if I do, so C squared is equal to A squared plus B squared minus 2AB cosine gamma. So it's sort of a Pythagorean Theorem on steroids, in the sense that you don't need a right triangle and you still kind of get the statement of the Pythagorean Theorem. This special case of it, when gamma is a right angle, then cosine of gamma is equal to 0, and you do get the Pythagorean Theorem, c squared equals a squared plus b squared. But this one is really nice because it actually works for any triangle. Another way to view this theorem would be to see this as a way of computing the angle between two sides of a triangle, knowing the lengths of the other sides, right? If I really wanted to, I could just recalculate this cosine gamma from this. So I'll solve this equation for cosine gamma. So what would it be? Let's see if we can do the algebra quite quickly. So if we take this to the left side, then c squared goes to the right. So that's a squared plus b squared minus c squared divided by 2ab. So there's sort of several ways to view it. One way to view it is that it allows you to compute an angle, to compute the cosine of any angle in the triangle if you know all of its sides. So we would like today to derive a spherical version of the law of cosines. So we start with a sphere, but this time I drew only 1/8 of it. So I put the x, y, and z coordinate system here, as you can see, and then I drew just one section of the sphere. So this is the sphere that's completely contained in the part of the x, y, z coordinate system where x, y, and z are all positive. Okay, and to make things easier also, let's suppose that we position, so we start with a triangle on the sphere, and we position the sphere in such a way that one of the vertices is actually the North Pole. So that's one of the vertices of the triangle C, which is the North Pole of the sphere. And also by rotating it or rotating the coordinate system, I can also ensure that another vertex lies in the x z plane. The third vertex is somewhere, I don't know, I don't have any influence or where to choose it, so I just put it here. Okay, so this purple, black, red triangle is the triangle of our interest. So I'm going to just do this very similar thing here. So this is capital C. So that's the vertex at the angle gamma, right? If I wanted to further decorate this triangle here, I would put capital C as a vertex here, capital A here, and capital B here. So it's all nice and symmetric. So I would like to then compute the cosine of this angle gamma using the sides of this triangle. So I have not yet marked the sides of the triangle, but how would I mark them? Well, this side here, of course, it's part of a great circle, right? That I will just mark by little c. This red part, that I would denote by little a. And the black part I would denote by little b. So these are length of these sides, which of course are just geodesics on a sphere, so parts of great circles. Remember that these lengths are actually the same as the measures of the angles. So this length is the same as the measure of the angle COB. So I'm going to denote this angle here. So one of the axes I already have, right? So I'm going to just put another one here, like this. And this is of course the origin O. So this A is the same as that angle over here. Similarly, if I want the length B, then I draw a line from the origin to A. And so you see that this length here is part of this great circle, and this is the corresponding angle B. Okay, so remember I use my lowercase letters for side lengths, which are the same as the angles at the origin, uppercase letters for vertices, Greek letters for angles. I'm just going to use one angle here, namely gamma. But it turns out I need one more piece of decoration here, because I'm going to deal with vectors. So I am going to actually denote, so look at this radius, right? It's a radius of the sphere that starts at 0 and ends at A. I'm just going to make it into a vector whose origin is 0 and whose endpoint is A, and I'm going to denote this vector by A arrow. Okay? And similarly, I'm going to use the B arrow here. That is going to be this vector. Note that A and B are actually unit vectors. So they have unit length, because the sphere here is, of course, S2, so that's a unit sphere. And finally, the vector from 0 to C, that's actually just part of the z-axis. So I'm going to denote that vector. I sort of don't really have a space to make this arrow here at the end. But this will be denoted by C with an arrow. Okay, I think that's enough decorations for this picture. And before we proceed with this, I wanted to make one more remark about computing angles between planes. So, going into here, on this side of the board, I drew two intersecting spheres. Sorry, two intersecting planes. The black plane and the purple plane. And they have a certain angle between them, right? The angle gamma. It turns out that another way, so this is, I just drew these angles sort of in a certain direction going from the black plane to the purple plane. Another way to represent this angle is to draw a normal vector to both of these planes. So I'm going to draw the normal vector from the black plane, sort of pointing in the same direction as the angle, so sort of here. Okay, normal vector, remember, is a vector that is perpendicular to the plane. But it can point this way or that way. So I'm choosing it to point this way, just like this angle here. And the same thing I'm going to do with the purple plane. However, the purple plane is horizontal, so the normal vector, again going in the same direction, would just be pointing down. Okay, and if you just look at these two vectors, so here's the black one, and here is the purple one, you see that the angle between them is the same, namely gamma. Right? Because all I have really done is I had that plane and then I just sort of added 90 degrees. And same, I had this plane and added 90 degrees. So the angular distance between these two planes is the same as the angular distance between these two vectors. So a vector between an angle between the planes is the same as the angle between the normal vectors. You just have to be careful that you choose them in the same way. So you don't measure the vector, you don't choose one pointing in that direction, one pointing in that direction, then you will get pi minus the angle. Okay, so we go back here. So remembering this, this thing about angles between planes, we now go back to our sphere. And we're interested in this angle gamma. And remember, we talked about that in one of the previous videos, that an angle inside a spherical triangle is the angle between the tangent line, of course, and that's the same as the angle between the planes that contain the corresponding great circles. There are two great circles here, right? One is the one that contains the arc A, and the other one is the one that contains the arc B. So these two great circles form a certain angle between them, right? So that angle is that angle gamma. So gamma is the same as the angle between the plane of great circle BC and plane of great circle AC. Okay? The great circle BC and the great circle AC, gamma, is the angle between these two planes. But that's the same thing as the angle between normal vectors to these two planes. So I can actually compute these normal vectors because I drew some of these vectors here on the picture for a reason, namely to be able to compute normal vectors. So let's look at the vector B and C, okay? And let's see what happens if I take the cross product of B cross C. The vector B is the vector from the origin to point B, so it lies in the great circle BC, in the plane of the great circle BC. And the vector C also lies in the plane of the great circle BC, because again it just goes from the origin to C. Right? In particular, I could just sort of cut out this little triangle here, and you see that B lies in that plane and C lies in that plane. So this, if you take cross product between vectors, you get a vector that's perpendicular to the plane in which they lie. So this would actually be normal to the plane of the great circle BC, except it might not be unit length. So if I wanted to get unit length, I just divide by its length. So this is normal vector to plane. I'm just going to write plane BC, right? It's the plane of the great circle BC. If I choose it like this, so the vector B goes first and then vector C, right? So that's like I'm going from B to C, so I'm sort of screwing things in. So the normal vector points to the left. Just going to write it here like this, that it's sort of pointing to the left. That's the normal vector. So to get the correct measure of the angles between the planes, I want the normal vector from to this plane to also be pointing in that direction. So that means I still want to go like this, so like that, right? So that means I first do A and then do C. I'm sort of screwing again in this direction. Remember, A is sticking out here, C is completely vertical, so I'm going from the sticking out vector to the vertical one, so I go in this direction as well. So then I get so I'm going to do AC, A cross C. Is the normal vector to plane AC. And because I chose them consistently, the angles between the planes is the angle between these vectors. So gamma is the angle between these two vectors. right. So now I want to compute cosine of gamma. And for this, I'm going to use the formula for the dot product. So I can already erase this. I'll still leave for you the picture so you can see what's going on. Right? So if I do a dot product between these two vectors, so I do B cross C dotted with then let's think what I get. What is the dot product between two vectors? It's the length of the first vector, but what's the length of the first vector? It's a unit vector, so the length is 1. So 1, that's the length of this, right? The length of this vector. Times the length of the second vector, but that's also 1. Times the cosine between the angles. Remember, dot product. A dotted with B is the length of A times the length of B times the cosine between the two angles. But what's the cosine between these two angles? Well, what's the angle between them? That's just gamma. So that's just going to be cosine gamma. Okay, reading it from the right, I get my formula for cosine gamma. Except that's not really in terms of what I wanted. I wanted it to be in terms of lengths of sides. So these lowercase letters A, B, C, while I have it in terms of some nasty cross products. Okay, but well, no worries. We're gonna turn this into what it's supposed to be. So first of all, let's take care of the denominators. Because I know how to compute the length of a cross product, right? It's the length of B times the length of C times the absolute value of the sine between these two angles, between these two vectors. Okay, few simplifications here. What's B? Well, that's the vector from the center of the sphere to the circumference of the sphere, to the surface of the sphere. So that is the same, length is the same as radius, so this is 1. And so is this. Now my sine, all my angles are between 0 and 180, so sine is already positive there, so I can just forget about the absolute values here. So it's the question, what is the sine of the angle between B and C? Let's see, B, C. What's the angle here? Oh, that's A. Oh, so that's sine A. So that denominator here is sine A, and similarly, if I try to do this, that's the length of A, which is 1, times the length of B, which is 1, times times the length of C, which is 1, times the sine of the angle between them, but the angle between them is B. Okay, so I converted the denominators into something that can be expressed in terms of these lowercase letters. So now the numerator. So I really look at this. I'm looking at B cross C dotted with A cross C. Okay, and for this, you may recall we had that sort of somewhat crazy formula that told us how to do a dot product of two cross products. It was first this dotted with that times, as another number, this dotted with this minus this dotted with that times this dotted with this. Okay, if you watch the video about the review of dot product and cross product, this was the one formula that we didn't derive there. We talked about it there. Let me just double check. That's this times this times this times this minus this times that and this times that. Okay, so what about these dot products? We can actually compute them now. B dotted with A. That's the length of B times the length of A times times cosine between these two angles. But all these angles, look, A, B, and C, right? They're all the radii of the sphere, so they all have length 1. So I don't have to worry about the length. All of these will just come out as some cosines. So B dotted with A, that's going to be cosine of the angle between B and A. So, oh, that's C. Right? So that's cosine C. Right? Again, maybe I'll just write it for this one case here. This is the length of B times the length of A times cosine of the angle between B and A. This is 1, and cosine between B and A, that's the one you don't see here written down at the bottom, but remember cosine between, that will be the cosine between this length, and that's the same as the length of the great circle, of the part of the great circle, right? So that's cosine C. C dotted with C. Oh, that's the length of C, which is 1, times the length of C, which is 1. And then the angle between C and C, that's 0. Cosine of 0 is 1. So that whole thing is just 1. So it's cosine of C only from here. Minus B dotted with C. Length is 1. Length is 1. And the angle between B and C, that's A. So that's cosine A times length of C, length of A, times the cosine of angle between them, times cosine of B. Okay, and putting it all together, we have our formula. So, cosine of gamma it was, these two are in the numerator, so that's cosine C minus cosine A cosine B divided out by the length of these two vectors, that was sine A sine B. This is the law of cosines. On a sphere. Okay, but now let's step back a little from this and think about what on earth does this have to do with the classical law of cosines, which, let me just remind you here, the statement of it was we had a triangle let this be the angle gamma, so this would be CAB, and the law of cosines said that c squared is equal to a squared plus b squared minus 2ab sine gamma. Now this, yes, it does express cosine of gamma by the lengths, but it doesn't look anything like this. Well, first of all, why should it? It's a sphere, not a plane, so maybe things look differently. Except for one thing, namely, if the triangle is small enough, remember that things should resemble what happens on a plane. So let's now assume that these lengths A, B, and C are small. In that case, I'm going to use the Taylor series for sine and cosine to get good approximations of them. Then, if you just remind yourself the Taylor series of sine, that's sine x, that's x minus x cubed over 3 factorial plus x to the 5 over 5 factorial, and so on. But if x is really small, then only the first term, the first non-constant term will matter. So it's really the sine A is then approximately equal to A. The next term would be minus A cubed over 3 factorial, but we just ignore all the higher order terms. So similarly, sine b would be approximately b. What about the cosines? Okay, so how does a Taylor series for cosine start? It starts with 1. Well, that's not a good enough approximation. So it starts with 1. What's the next term? Well, that's minus x squared over 2 factorial. So minus c squared over 2. And I'm not going to go on because the next term has 4th power and so on. So these are small compared to these when c is small. All right, so let's now see what this says if we use these approximations. So for small a, b, and c, we get the cosine of gamma is approximately equal, cosine c is 1 minus c squared over 2, minus cosine a will be 1 minus a squared over 2, and cosine b will be 1 minus b squared over 2, and everything will be divided by a, b. Well, first of all, look, squares appeared, right? Just like in the classical law of cosines on the plane. Let's do the simplification here. So that is equal to 1 minus c squared over 2. All right, let me just multiply this out. So that's going to be minus 1 plus a squared over 2 plus b squared over 2. And finally, minus a squared b squared over 4. Everything divided by ab. But just as the argument went a moment ago, this now is small. So is very small. Compared to the squares, this is even smaller, like another magnitude another order of magnitude smaller. So compared to a squared and b squared, this is very small, so we can ignore it. So we get cosine gamma is equal to, well, these ones cancel. So I get a squared over 2 plus b squared over 2 minus c squared over 2. And if I multiply the ab on the other side, I get ab cosine gamma. And if I multiply both sides by 2, I finally get a squared plus b squared minus c squared. This is all approximately equal here, right? Equals approximately 2ab cosine gamma, which is, look, exactly that.